We are very privileged to have some time with Professor Norbert Morgenstern and Dr. Evert Hoek and ask them some interesting questions from their career and from their perspectives. So that's what we're going to do right now. So my first question will go to Professor Morgenstern. Professor Morgenstern, you have achieved a lot in your engineering career. You've done a lot in geotechnical engineering and slope stability analysis. Can you tell us which achievements you cherish the most, the ones you're most proud of?
Well, I think my career has had teaching, research, and practice. And I think one of my biggest achievements are the success of my students. That's something I get a great pleasure. I meet them now on consulting boards because they're getting on a bit, and it's just wonderful to share the achievements that they have made, and I'm very proud of that. From a technical perspective, I think my longest and probably most challenging technical issues has been involved in the oil sand industry in Alberta. And we've had major tailings dams, Syncrude and Suncor and other of the big operations there, which have had a series of complicated foundations, difficult issues, liquefaction, and all the other issues. I've been on review boards there for decades now and have great pleasure in the success the industry has had in that part of their technical challenge.
Excellent. Thank you very much. Dr. Hook, can you please tell us about an engineering project that impacted your rock mechanics or engineering development the most?
I think rather than talk about a specific project, I'd like to talk about a group of projects which are all the same. The design of large underground caverns for hydroelectric development. And the cavern itself is the center feature of typical projects of that kind, and the design has to be very carefully done. And what I'd like to do is draw on one particular project and then broaden it a little bit. The project I'm talking about is a project called the Mingtan hydroelectric project in Taiwan, and the projections had been good for the site, and there were no major problems, but you have to go through a very careful process in designing a cavern of that size. There were a series of faults running parallel to each other, dipping at about I would say 45 degrees, which is not a good angle for faults to dip at when you're going to mine through them. And the first thing that we did was to rotate the cavern so that it was normal to the faults. The original design, it had been in a different orientation. It meant a little change to the hydraulic tunnels, but that was not as big a problem as it would have been having to deal with the caverns with inclined faults through them. So we just had to deal with one inclination, and the cavern was successfully mined by doing a pre-support of the roof from tunnels excavated above the cavern roof, so that we'd suspended the whole roof before we started, and then mined down in a series of about 9 steps. We're talking about a cavern of 40 meters high and 25 meters span, that sort of dimension. So this is a very big hole in the ground. And the technology has now developed, I would say, very well. And we have good numerical models available of all kinds to analyze the 3-dimensional stresses around the tunnel and any potential failures. And the big issue that we have to analyze is what support or reinforcement do we put in to basically ensure that that cavern is going to be stable for its projected life of maybe 50 years. And I think we're in a good position now to do that successfully.
Thank you very much, Dr. Hook. The next question I have for you is, what should tailings engineers worry about most in the coming years? For example, should they pay more attention to numerical modeling, critical state mechanics, or reliability assessment?
This has been a large part of my life over the last decade or so, the issues that we've had in tailings dams. I think it's important, and I think the industry, the profession, I think the mining industry is learning that tailings dams are not the same as water dams. They evolve under very different circumstances, and they've been exposed to probably the lack of understanding of those circumstances for a very long time. And I think the first thing we've had to learn is to change the way we think about safety and the way we can create safe management systems, as opposed to rely on the traditions of water dams themselves. My own involvement has brought me into leading or participating in forensic investigations for a very large number of these facilities. And I think the big takeaway from this, which is now filtering out into practice, is the errors that we have made in our geotechnical profession, either by underestimating the complexity of the natural foundations, either by not really understanding the challenge of static and dynamic liquefaction, and a host of other errors of understanding. So while traditionally uncertainty has been classified as a method uncertainty and a data uncertainty, the involvement of human error, which I now call embedded ignorance due to our own failings as we've evolved in understanding the mistakes we've been making, has become the biggest challenge. And I'm pleased to see that the industry is certainly at the leading edge. The major companies are understanding that, are now committing to a safety culture with a very high degree of zero fatalities and zero significant environmental impacts. The profession is responding to that through its training and expansion, and the resources are now structured within the large mining companies to support a safe management process. It's a system that has to be implemented, and we've created the elements of that system in a number of studies, such as the Good Practice Guide, supported by the International Council of Mining and Metals, and these things are now being put into practice as we speak. There'll be a major evaluation of their successes when reports have to be filed as required by the global standard that's now extant, which all the major mining companies have agreed to participate in, and we'll be able to evaluate that later this year when these risk analyses and reports on better safety compliance are submitted for, not necessarily for international review, but they'll be internationally available. So the biggest change is now the recognition of human error that's contributed to the major uncertainty and the evolution of design, construction procedure methods, support at the highest corporate level in the mining industry. And from my technical perspective, the implementation of what I call performance-based design to execute and check through all phases from conceptual design all the way to closure. So this is the big issue in that world.
Thank you very much, Professor Morgenstern. What checks and balances do you use to ensure that you do not make mistakes? Or at least, what do you do to minimize errors?
That's an interesting question. Obviously, in doing the design of a structure such as a tunnel or a major mine slope, you have to ensure that you have adequate data. And so you have to go through the process of asking yourself, what is it that we need in the way of number of boreholes or number of kilometers mapped along benches and so on. And this is a question very largely of economics, and some people realize that they've got to put the money into it. Some are more reluctant to do so. So there's a big issue with the amount of information that we start with on major projects that we have to recognize. Having got the data, though, one has to go through a careful design process. Unfortunately, today we have an increasing amount of sophisticated software, both 2- and 3-dimensional, which enables us to analyze virtually any structure that I could visualize on the surface or below the surface. And that's extremely important. How do you check the correctness and the possibility of mistakes? Obviously, you have to have somebody review things for you, but ultimately it comes down to what happens when you start building the actual structure. Typically in a large underground powerhouse, for example, you would start by mining the access tunnel first, right down the center of the top heading, because that gives you your first glimpse of the real rock mass. You're not dealing with core or interpretations, you're dealing with the rock mass that you're going to work in. And that's pretty much accepted now, that you have to have a full excavation of significant size, that you can work with the rock and learn how it's going to behave. Because no amount of research in the lab or reading is going to tell you those facts. And that's become common practice now. So that would be my answer for the way that you determine whether you're close to or whether you've got to make some serious corrections. Fortunately, most of these projects are long in duration. I'm typically talking about big projects, not a 500 kilometer or 500 meter tunnel in some city location where you might have to gain your information in other ways. I'm talking about big projects in the field. And they're big enough that you can take your time and do preliminary tunnels to explore what's going on and make any corrections that you have to in your technology from those.
Thank you. Everyone expects AI, artificial intelligence, to significantly change the way we do things. Can you foresee how it will impact geotechnical engineering, research, and practice?
Well, that's an interesting question. And of course, that's one of the things we all chat about these days. So I'll respond in several ways. The last year, the International Society of Soil Mechanics at its international conference in Sydney created a time capsule. And many people were invited to make presentations to be recorded and opened in 50 years and so on. And as a past president of the International Society, I was one of those. And I recounted about how the society had evolved during my presidency and some of the things that have transpired since that time, some 20, 30 years ago. And then put into the time capsule, when you open this, one of the things you should ask yourselves is, how has AI affected the conduct of geotechnical engineering? So part of the answer to the question you put to me, I put to the same community, but to be answered in 50 years, whereas you're not giving me that liberty at this time. Let me say I'm an amateur student of the emergence of AI, and as a grandfather, one of the actions I've taken over the last couple of years, I've got a number of grandchildren going into university and making career choices, is to make some effort, even though they're doing diverse things, make some effort about how AI is going to be impacting your choices as you evolve. So I think I'm sensitive to the impact and also the ambiguity and the lack of understanding we all have about where we're going, with this unstoppable train. My own personal reaction to the involvement of AI is optimistic, as opposed to some who are pessimistic. I remember, I go back to the time when computers first came in the beginning of my professional career, and wow, that was going to be a disaster and so on, but of course it was a huge wealth creator and a lot of drudgery disappeared with the evolution of digital computing to the capacity that it has today. I have the same attitude that AI will, certainly it's going to eliminate a lot of kinds of jobs, but it's going to create jobs that are going to be higher valued. I think that that we're all going to be seeing a fairly rapid decline in population rate, which will ameliorate the lack of employment and the impact of that on the industry. But in terms of our own activities, I think that it'll be a strength if we learn how to use it in terms of interpreting and integrating data. I think that we'll be unlikely to be challenged at the judgmental aspects I think the burden of judgment and integration of geological considerations and the like will be enhanced by that. But I think there'll be fewer eyes. I think some of the more routine activities that are part of our profession today will disappear or be managed by some kind of focused AI activity, which will create a greater burden on the remainder to know more, to do more, to manage safety with greater care than we've had in the last decade. So there'll be some losses, but I think the losses will be compensated positively by the gains, both in our society and our profession. That's my optimism at my age.
Thank you very much, Professor Morgenstern. Dr. Hook, what are your thoughts?
Well, I listened with great interest to what Nordi has said, and I agree entirely with him. So let me talk about what I think the practical impact's going to be rather than the overall concept. I don't see it being immediately useful in answering some of the complex technical questions, because ultimately AI, somebody has to tell it what questions to ask, and we don't know what those questions are in some issues at the moment. However, I think there are several areas where it could be greatly of great assistance to us, and one of those is something that we always encounter in major projects in tunnels or open pit mines or slopes or whatever, and that is the huge volume of data that we are missing. In other words, if you're going to mine a tunnel 10 kilometers long and you've got 3 boreholes along the route, there's no way that that's adequate information for you. Where I see AI being enormously useful is in assisting us, provided we can find out the right questions to incorporate into the programs, in interpreting geological information. We never have enough of it, and the interpretations that are done, that I've seen done, can be very variable in quality, depending on the staffing. And this is going to be a major issue for us, that we have, I think, a deficiency of people who are well trained in engineering geology, deficiency in numbers of those people to cope with all of the information that we're going to have to deal with. And I see AI coming in as a great assistant in that particular area. That's probably the most important. I'm more skeptical about its ability in terms of the design process itself. I think we still have a long way to go to establish what are the design elements we've got to build into. I'm talking about rock structures like underground caverns or tunnels or large slopes. We haven't figured out all the questions that we need to be answering yet, and we can't ask AI to do that for us until we can tell it what to ask us. But I see it as enormously valuable in doing many of the mundane tasks that are difficult to staff and difficult to accomplish in our field.
Excellent. Thank you very much. Just as an aside, does that include core logging? As the mundane task?
Absolutely. Absolutely. I mean, not necessarily asking AI to core log itself, but to interpret the results of core log and particularly to project them between boreholes, which, believe me, on site can be very far apart for the size of projects that I work on.
Professor Morgenstern and Dr. Hook, thank you so much for giving us this time. We'll cherish your insights for many years to come. Again, thank you on behalf of the entire geotechnical community.
Thank you very much.